Hi, my name is Miss Oliva, and I'm here to give you some help with symmetry and piecewise functions. And if you're in my course, this is part of 1.7. So let's get started. So first is symmetry. There's three types of symmetry that they're going to be talking about in this unit. It's symmetry with respect to the x-axis, which means the top and the bottom are the exact same as if you had flipped one side over the x-axis. Then there's symmetry with respect to the y, same thing, but this time over the y-axis. And symmetry with respect to the origin, which is kind of like flipped over the x and then over the y. And I'll explain in a second. So this graph, if you see, this side is the exact same as this side. So if I had drawn this and then flipped it over, I would get this. So this is respect to the y-axis, because it's the y-axis that it would have been flipped over. So this one, same thing, right? That side got flipped over to there. So it's symmetric with respect to the y-axis. Next two, if you'll notice, look like they got flipped from the top to the bottom or vice versa. So they're the exact same on both sides with this in the middle, which is your x. So they're symmetric with respect to the x-axis. And this one too, if I had drawn it perfectly. All right, and then finally, the weirdest one is the origin. It's a little harder to kind of picture, but the way I think of it is if I take one part and I flipped it over the y and then over the x, would I get to the other part? And so do you see that that would work with this? Or you can think of it as being flipped over kind of a line that goes through the origin. Either way. Okay. So when you don't have a graph, how do you tell if something has symmetry? Well, there's two types of functions. They call one an even function, and that's a kind that has symmetry with regards to the y-axis. And there's some called odd functions, which have symmetry with respect to the origin. So in this type of question, there is no type of function that means it is symmetric with respect to the x. So if that's the case, you would just say neither. So these are the two options if it gives you an equation and asks about what type of function they are. So the easiest way to do these is to use this rule. What this rule is saying is if you take whatever function you have and plug in negative x's everywhere you see an x, would you end up with the same thing that it started as? If that happens, it's even. If you do the same thing, plug in a negative x anywhere you see an x, but it turns out to be the exact opposite of the entire function you started with, then it's odd. So let me show you, because I know that's a little confusing. So I'm going to find out what happens when I do this. Well, be careful and make sure you're only plugging it into the x. So I'm going to use a parenthesis to show that this needs to be raised to the fourth power plus 6 and a negative there too. So negative x raised to the fourth power becomes positive. And same thing within an absolute value sign. So do you see that I ended up with the same thing I started with? That's what this is saying. Did you plug in an x but get the same thing you had when you started? That is what happened here. So this is an even function. Excuse me. Thank you. Origin. Let's see what happens here. Let me go and again plug in a negative x everywhere there is an x, but be careful that you use parentheses if you need to. And then we're going to simplify this and see what we get. Okay, Sorry, I had to pause for a second. Okay, so now to reduce this. If I raise a negative to an odd power, the negative is still going to be there. So this is going to become negative 5 times negative x to the 5th, which means it's really going to turn into a positive 5x to the 5th. Same thing here. This negative raised to the third power will still be negative. So when I multiply it by that 4, it will become negative x to the third. And then finally, plus a negative x, I can just say minus x. So comparing what I started with to what I ended with, do you see that the entire thing is the opposite? So it doesn't mean everything has a negative, right? Because the 5x to the 5th doesn't have a negative now. But since it used to have a negative and now it doesn't, that's the opposite. 4 was positive, but now it's negative. So that's the opposite. So everything is the opposite. So that means it is an odd function, which means if I graphed it, it would have some kind of symmetry across the origin. Okay, so that's an example of what it would look like if you have an even, how it works. And here's an example of an odd function. So how about if this was the question, and they just said, could you please tell me, is this one even, odd, or neither? So first of all, what would neither look like? Let's say in this example, the negative 5x to the 5th became positive. This became negative, but that final x for some reason stayed positive. That wouldn't be even because it didn't all stay the same, and it wouldn't be odd because not everything became the opposite. So that would be an example of neither. So let's see what happens here. If I plug in my negative x and then simplify as much as I can, I want to see if it becomes the exact same thing I started with or the exact opposite or a mixture, which would mean neither. So up top, that would definitely become positive x squared. On the bottom, I would have a negative x minus 6 squared. I guess let's reduce this a little bit so we can really see what's happening. So on the bottom, we really have this, which means on the bottom, we really have 7 times x squared minus 12x plus 36. And so I could distribute the 7, but it wouldn't change the signs because that's all I really care about are the signs. So on this one, if I did the same thing, I would get x squared plus 12x plus 36. So a slight difference. If I'm comparing my original one to my new one, some of it's the same. Top is definitely the same. 7x squared, if I were to multiply, would be the same, but that middle term is different. So some things the same and some different means it's neither. It's not even and it's not odd. Okay, piecewise function. A piecewise function means there's different things happening at different parts. If you graph it, it would look something like maybe this is happening here, maybe a part of a parabola is happening here, and then a straight line here. So it's in pieces. Sometimes those pieces connect, sometimes they don't. So that's what a piecewise function means. But here, before we worry about the graph, we're just worried about what this means. This means that if you have an x that is less than or equal to -2 and you want to plug it in, you would plug it into this. If you have an x that is anything between -2 and 3, you would plug it in this middle function. And if you have anything greater than 3 or equal to 3, you would plug it in here, but that's going to be weird because there's nowhere to plug it in. So we'll see what happens there in a second. So if I wanted to do h of -3, -3 is less than -2. So I would need to plug it in here. The absolute value of -3 is 3. So I really have -9 plus 7, which is -2. If I want to find h of 3, 3 is not in this section because there's no equal sign there. So 3 would be in this bottom group. But since there's nowhere to plug in the x, anything in that last group is going to be 4. -2 is also in this top group. So I would do -3 times the absolute value of -2 plus 7. Since this becomes positive, it would be -6 plus 7, which is 1. 0 is finally in this middle section, right? 0 is between -2 and 3. So I plug it into the 5x, so 5 times 0 plus 3. And finally, f of 4, I would plug in again into the last one, but again, nowhere to plug it in, so it just stays 4. So that's as far as just plugging numbers into a piecewise function. Now let's talk about graphing it. So here it's saying we kind of have two different functions, but let me write this as a piecewise function. So let me call it h of x and say kind of like up top, h of x is this, but only when x is less than 0, and it is this when x is greater than or equal to 0. So how would I graph that? Well, first of all, I'm definitely changing from the 1 to the other at 0. So I'm going to maybe just mark that with a dotted line, because dotted lines on graphs really mean nothing's here, but it's just for me to see that I'm going to be doing one thing over here and a different thing over here. So what does 3 absolute value of x look like? Well, remember the absolute value graph was a V. I'm going to use pencil here. It's a V that normally starts at 0 and goes both ways, right? This 3, though, is going to make it stretch vertically. So instead of up 1 over 1, I'm going to go up 3 over 1. Up 3 over 1 on both sides. So this is what the real absolute value graph looks like. But remember, we only want to draw this where x is less than 0. So we don't want anything happening over here. Now, what happens at 0? We don't want that to be a part of this graph, right? So right now, it's like there's an open circle there and going this way forever. Okay? Now, starting at 0, we're going to switch to a square root graph. So since that starts at 0, I'm now kind of covering up that open circle, which happens sometimes, but not always. This could have been an open circle, and then my next graph could have started up here. So sometimes they don't overlap. But if they do overlap, then where I had an open circle, I'm now filling it in to draw this. So remember that we go over 1, up 1, over 4, up 2, because the square root of 4 is 2. So this is one example of a piecewise function that happens to connect. But again, they don't always. There could be gaps everywhere. Like in this example where I had 3 separate things and then none of them connected. Okay, now we're going to look at what this looks like on the homework, because there's some buttons that are kind of weird to use. So I would definitely watch me do this unless you've already done your homework and it was easy for you. Okay, so this is similar to number 11. So number 11 first wants us to draw just this part. So draw just this part for when x is less than 0. So this is a V graph, but there is no absolute value option over here with a V. So I'm just going to draw a straight line on the part I want on the left. So I'm going to use the line. I'm definitely starting at 0, 0. And then since there's a negative out front, instead of over 1, up 1, I need to go down 1. So starting at 0 and going to the left, this is what I want, right? But I do not want any of this line, because that's not even right for the absolute value. It would have been the V going down. So I definitely want to get rid of this line. So that's where these scissors come in. I'm going to say that I want to cut this graph. And the first thing I want to say is, where do you want it to cut? Meaning, where's the part where you want to stop graphing? So that would be 0, 0. By putting in 0, 0, I'm now kind of splitting this graph in two parts, where if I wanted to erase something, it's not going to erase the whole line. You see that? So I could either erase this part or I could erase this part because I cut it in the middle. So that is this graph, but at 0, since we don't have a line under this to include it, I do need to show right now that there's an open circle, because right now I'm only graphing this. So that would be that part. Now for the absolute value, I'm going to start at 0. So again, 0, 0. But there's a 2 out front. So instead of going over 1, up 1 like I normally do, I'm going to go over 1 and double it. So go up 2. So this is what I want happening, starting at 0 and going on. So now they're just going to ask me to put it together. So line from here going down. I'm going to cut it in the middle. I'm going to erase the part I don't like. And then I would put an open circle, but I already know that in this case, it's going to be covered by this. So no point in putting an open circle. Over 1, up 2. So they overlapped in that middle part. The open circle and the closed circle overlapped. Okay, now let's look at 12 because it's a little different. All right, for 12, we have an absolute value graph again, but this time we're not starting at 0, so it's not going to just be one nice line. They want us to start at 3. So what that's going to mean is we're going to have some of the V going down and then it going up. So I'm going to use the line part first to do kind of what we did before, starting at the 0, 0. And since this is just the normal absolute value, going over 1, up 1. So this time, since they gave me the option to just do array, I don't have the whole thing. So I don't need to erase anything. But I do need to understand that I need to keep going with this absolute value to the right until x equals 3. So I'm going to do a segment this time, since it's not going to go on forever, starting at 0, 0 and going up 1 over 1 until I get to 3. So do you see how this is the absolute value graph, but stopping when x equals 3? And I would put an open circle there, but I'm not sure if it's going to be overlap. No. So let's just keep going. So now I'm going to graph, starting at 3, this line, negative x plus 6. Well, that's kind of confusing how to graph that, because you would start at 6 normally, and that's part of what I don't want. So I'm going to plug in 3 to see where would I be at this point where I want to start it. So if I plug in 3, I get negative 3 plus 6, which is 3. So I was correct in my thought that it is overlapping again. Okay, now where do I want it to go? Well, the slope of that line is negative 1, so down 1 over 1. And that should be it. Okay, let's go back to my notes for a minute. Next type of thing, next type of graph that maybe you haven't seen before is something called a step function. Okay, it's called a step function because you'll see in a minute it ends up looking like little steps. But this is also called a greatest integer graph, and you'll see why in a second. What these symbols mean are, if you put in a whole number like 1, you're just going to get a 1, right? Because nothing else is happening. So 1 equals 1. But when you put in something else like 1.2, it doesn't want us to keep the decimal. It wants us to kind of round down, always down in this case, to the integer under it. Meaning for 1.2, we could either go down and make it 1 or go up and make it 2, right? So they always want you to round down. So 1.7, even though that's closer to 2, I'm still going to round down. So my answer is going to always be 1 with anything starting at 1 and going up until 2, because at 2, it will jump to 2. Then anything between 2 and 3, we're going to go round it down to 2. But then again, when you get to that next integer, it will jump. 3.5 would go down to 3, 3.9, and 4 would jump. So what is that going to look like? So 1, 1 is definitely one of our points. And then if all these integers are going to continue to be at 1 until 2, where it jumps up here, the easiest way to show that is just to put that solid circle and do a line going to where it jumps, make it an open circle. Because that means 1, 1 is one of our answers. Anywhere in between here and here, it's going to be whatever 1 until this spot is where it's going to jump. Right? And then anywhere between 2 and 3, it would stay 2 until here. That's where it's going to jump. See how it looks like steps? And so you can just keep going the other way as well. Because sometimes the negatives are a little confusing, because if you have something like negative 0.5, we want it to round down to 0, but really negative 1 is the lowest integer. So the negatives can be a little confusing. So it's kind of easier to start with the positives and then just follow the pattern. Okay, so I'm going to show you this one on the homework as well. It is number 14, just to show you how it looks. So you have to be careful because they're going to give you a range or a domain to put it on. So they only wanted me to graph this from where x is -5 to where x is 4. And this time there was something going on in there where when I plugged in each x, I had to add 2 before I did that rounding down. So let's just try another one. Okay, so let me start with some positives. So I'm just going to start with 0. So what would happen at 0? Well, I would plug it in, I'd get 0 plus 4, and then I wouldn't need to round that because that's an integer. Now, everywhere from 0 to 1, that same thing's going to happen, but at 1, it's going to change, because if I plugged a 1 in there, 1 plus 4 is 5. So at 5, it's going to jump to there. Okay? Oh, that should be a line. Okay. So you can see the pattern, and I'm at 2 now, which is where it wanted me to stop. And it had a parenthesis, which means it doesn't want me to actually hit 2, and that's fine because I have an open circle there. So it worked out fine. So I'm just going to continue this pattern until I get to where x would be 5. Just continue my steps until I get to where x would equal 5. So I'm at -4 now. Sorry, I mean -5. And now I'm ending at -5. So now I just need to go back and make sure I have open circles on all these spots, because that's where it was always jumping to the next number, and solid circles on the left, because I do actually want to point there. Okay, do this correctly, should look like a nice little set of steps. Okay, all right, one last one, word problem. If we had a word problem like this, the way we could set it up, since kind of two different situations are happening would be to use a piecewise function. So first, let's try to understand what's happening in this problem. A cell phone plan charges $49.05 per month plus 14.02 in taxes. So doesn't that mean every month you pay both of these no matter what? So let's add them up and see what that would be for a month. 49.05 plus 14.02. Okay, so every month we owe this no matter what, plus 20 cents per minute for calls beyond the 300-minute limit. So only if we make more than 300 minutes worth of calls do we have to do this 0.02 thing, which basically means 20 cents, right? That's 20 cents. So in one case, we wouldn't have to do that, correct? So if we talk 300 minutes or less, because this says beyond the 300-minute, then we only have to pay these two things, our monthly charge and the tax. So this is one of my equations, just that, no X involved, because it's just this flat fee. But when would that happen? When X, our minutes, so we're going to call X the amount of minutes, is less than or equal to 300. And we can even go further, because since X in this problem stands for an amount of minutes, I hope you agree that we could never get into the negative numbers. We can't use our phone for -2 minutes. So I'm going to say even more that X has to be between the 0 and the 300. But it can be 0 and it can be 300. So that's why I need to use the less than or equal to, less than or equal to. So that's one case. If you talk anywhere in between 0 and 300 minutes, you only pay this no matter what. That's it. So the other case is going to be if X is larger than 300 minutes. In that case, we still have to pay this $63.07, but now we also have to pay 20 cents times however many minutes. But be careful, it's not just our X. Because let's just think of an example. If we talked 301 minutes, I wouldn't put 301 in here, right? Because we only have to pay 20 cents for the calls that are past the 300. So whatever our X is, our total amount of minutes, we need to subtract that 300 to make sure we're only paying for those minutes beyond the 300. So this is a tricky one, but now you've seen it done. So you can try the one on the homework that will be very similar. One case where your minutes are somewhere between 0 and whatever limit they gave you, and it would just be those set costs. And then the other part would be if you are beyond those minutes, you'll have the set cost plus 20 cents per whatever amount you went over. So that's your X minus whatever was the limit. So in our example, if we talked on the phone 301 minutes, 301 minus 300 is just 1, and that makes sense, right? I would only have 1 minute where I went over. So I'd have my set cost plus the 20 cents times 1. Okay, I hope that helped. Let me know if you need any more help or have any other questions on this section.